Now there's one little trick that we just need to have a quick look at. When you're dividing items into equal sized groups, there's a few things that can mess you up if you don't consider them. Now we've already learnt this complementary rule where n choose r is exactly the same as n choose n minus r. And that's nice and easy to think of if you look at an example. If we have something like, say, 6 choose 2, then we can see that if we've got 6 items and we choose 2 of them, we're effectively not choosing the other 4. And so there's just as many ways that you can not choose 4 things as there are ways of choosing 2 things. So that makes a lot of sense. But when we're dividing items into equal sized groups, often we're going to overcount. Now, we'll look at an example and just literally write things out old school so that we can understand why this happens. Now, if we have, say, 3 items and we want to choose them from 6, it's natural to say, well, there's 6 choose 3 ways that we can choose those 3 items. That's 20 different ways. But what we need to consider there is that we're just choosing those 3 things. Let's imagine there's 6 foods that we could eat for dinner and we're only allowed 3 of them, so we're going to choose the 3 things that we're going to eat. We no longer care in that context about the things that we haven't chosen to eat. We're looking at what the meal is that we've chosen. It's quite different though if you say divide 6 items into 2 groups of 3, because when you choose 3 items, you've effectively not chosen the other 3. Now, in this first context of just how many ways can we pick 3 things, sure, there's going to be 20 ways. But the number of ways to divide 6 items into 2 groups of 3 is going to be halved. And the reason that it's halved is that every single group of 3 that we could pick, there's another group of 3 that we've left behind that if we were to pick that another time, it's basically the same thing. So we've overcounted by a factor of 2 factorial. Why 2 factorial? Because we're dividing things into 2 groups, and so everything we choose has 2 ways that we could choose it. We could choose the things or the not things, if that sort of makes sense. Now here, I've actually itemized all the ways that I could divide 6 items, and I've just called them A, B, C, D, E, F, into 2 groups of 3, just to prove it to you. Now, start with the most simple and make yourself some sort of list that makes some sense. You'll notice there's 4, 3, 2, and then 1 in each of these lists. ABC with DEF, that's one group split. Now if I go down and say, well, A is definitely in it and so is B, it makes sense to consider joining in C, D, E or F. And here I've just put the leftover letters in alphabetical order. Next it makes sense to say, well, what if B isn't in it? It's A and C. Well, it could be with D, E or F, and again I've put the leftover letters, A, D's and all the AFs. Now you might think, all right, what if A isn't in that first grouping? Don't you have to go to B? But if I was to write down a list of B's now, what do you think I'd start with? B, A? Well, I've already got all the ABs. B, B? No, we can't repeat the B. What about B, C? Yeah, sure, let's do that. B, C, D would come first, wouldn't it? Oh, except I've already got B, C, D. It's over here. That got chosen when I effectively also chose A, E, F. So see how that one's already picked? And if you keep looking just to check you've picked everything, the next one would be BCE. Sure enough, we've got that, and BCF. Then if you consider what would come after that, well, the BDs. We've already got BDE and BDF. Where's BDA, you wonder? Way back here. Already got it with ABD. See that? So all of the selections that you can think of making once you've got this list of 10 are actually already there. They just might not be in the first side, they might be on the second side. Now a similar sort of thing happens when we divide items into equal sized groups and we get more than just 2 groups. It gets really complicated at this point though, so this is double black diamond sort of stuff. Now I've changed the question here a little bit. The number of ways that we can choose 2 items from 6, well that's straightforward. It's just 6 choose 2, there's 15 ways. But that's if we're only caring about which 2 items we have and not what we're doing with the leftovers. It's quite different to this question. The number of ways that we can divide 6 items into 3 groups of 2 is, well, I've gone ahead and just listed them. Now this is an old school method. It's a good fallback if you're stuck. Now, sometimes when you start listing things, you won't actually have to list all of them. By the time you get to here, you can sort of see a pattern sometimes and you won't need to do the whole lot. But if you're ever unsure of how something works and you've got time, listing them is a good way to figure out a method, and then you can do a harder question using that same sort of thinking that you've got from looking at the easier one. So here I've divided the letters A, B, C, D, E, and F into 3 groups, and I've listed them sequentially, all the ABs, ACs, ADs, AEs, and AFs. And then reasoning that there must be 5 different partners that A could have, I've sort of got 5 groups there. Now, once I've chosen my 2 items out of the 6, what am I going to do with the other 4? Well, they can be arranged 4 choose 2 ways, and that's 6 ways. But half of those ways are going to be exactly the same. We've just looked at what happens when you take 6 items and divide them into 3. So if I'm taking 4 items and dividing them into 2 pairs, there's not going to be 6 ways to do it. There's only actually going to be 3 ways. Now let's look at this one section so we can see what's happening here. If we've got C and D together, it's going to leave E and F. There's only one choice. So effectively choosing the next pair also chooses the remainders, or the 2 that are at the end. And there's only 3 things that I can do here with the C. I could put it with D, E, or F, because A and B are already used up. So it makes sense there's only 3 options. And then writing out what the leftovers are is the last thing to do. Now, if you get to the point where you've written all of these out and you think, oh, there's still so far to go, I've only done the A's, now I've got to do the B's, and then the C's, keep on going and going and going. No, you don't need to do that, because any pairing that you're interested in, you can see how many of them there are going to be. Now with ABs, we can see that there's 3 ways that the other 4 are arranged. Pick any other letter you like. Let's pick one. Let's say EF. What about if we needed to do all the EFs? Well, we've got EF, we've got EF, we've got EF. And in fact, there's 3 ways that the other 4 letters can be broken into 2 pairs when the when the E is with the F. Does that make sense? So in fact, this is all of the ways that we have here. 5 groups of 3, so we've actually got 15 ways. And coincidentally, the answer turned out to be the same as this one in this case. That's completely a coincidence. Now, what's going on here? How could we do a question like this without writing it all out? Well, what's going on is that there are 6 choose 2 ways that we can choose the first pair. Now, when we've got the 4 leftovers, there are 4 choose 2 ways that we can divide them up. But we need to be careful because we've overcounted. So we need to divide by the number that we've overcounted by. Now, what if we overcounted by? Well, there's 3 groups, aren't there, when we're dividing something into 3 pairs. And so those 3 pairs can be arranged in 3 factorial ways. So we've actually overcounted not by 2 factorial in the last example, but in this example, because there's 3 groups, by 3 factorial. So what that gives us is 15 times 6 on the top over 6 on the bottom. And coincidentally, we end up with that answer of 15. So now we've got a method that we could apply to those sorts of tricky questions.